Question 15. So, let us discuss about the thermodynamics which has which is from the GATE 2025. In question number 15, it is asked to find out number of independent intensive variables that need to be specified to determine the state of a system of a ternary mixture of at a vapor liquid equilibrium. That means he is talking about one vapor and two different liquids are simultaneously existing in a container. So, let us find out, to get one vapor and two liquids at the same time, then how many variables I have to specify, and we have to use the Gibbs phase rule. That means number of independent intensive variables that need to specify can be found from the formula C minus P plus 2, where C is number of components, P is number of phases. The phases are, you can see, vapor, liquid and liquid, two liquids and one vapor. That means number of phases are 3. Okay. And how many components are there? It is defined, it is a ternary mixture. That means number of components present will be 3. And diagrammatically, if we can able to find what is the significance of vapor liquid equilibrium can be analyzed from this figure. It is one such a graph where you can identify the things. Temperature is on the y axis, mole fraction is on the x axis. You have to identify such a point where vapor liquid equilibrium is existing. You can see on the left hand side it is a alpha liquid, let us take it as a first liquid, second liquid is a beta liquid, third is a vapor. And there is a certain point on the graph where you can find all the 3 components. You can see this center line, dot line, center point, which is in the black color, where exactly vapor and alpha liquid and beta liquid, all the things present on this particular point. So, at this point you can find what this is the temperature, this is the composition, what is a mole fraction of this. I mean, on the x axis it is a mole fraction of the beta liquid. Do not worry, its formula is very simple. That means graphically, if you want to find out, if we specify this particular temperature and this particular mole fraction of the beta liquid, you can able to get 3 phases are in equilibrium. One is alpha phase, beta phase and vapor phase. Other than this point, there is no other point where you can able to find all the 3 liquids at a equilibrium. Okay. So, it is a kind of explanation using the graph. Now, you have to specify, if you, that means degrees of freedom you got C minus P plus 2, which is equal to 2. That means you can specify this particular temperature and this particular mole fraction. So, you can able to find this vapor liquid equilibrium point. So, what are these 2 variables? You can fix either temperature and mole fraction, or temperature and pressure, or pressure and composition. Using any particular graph, you can able to identify at these, if you specify any of these 2, either temperature pressure or temperature composition or pressure and composition, you can able to find this particular point where vapor liquid equilibrium can be existing in a ternary mixture. Okay. Thank you. Let us move to the next. This is question number 16 in thermodynamics. The question is, the boundary of a system does not allow exchange of either mass or energy with these surroundings. Then the system is termed as which one among the options given? Example, you can take any example, keep a container consisting of water. So, the container boundary, the water is enclosed within the container. The walls of the container is called the boundary of this particular system containing water. Okay. Outside this container, it is called surroundings. There is no water flowing into this system. There is no water flowing outside the particular system, and the boundary is also insulated so that no heat can go into the container and no heat can come out of the container. That means neither mass is going in or out, and nor going in, energy going in or out. So, in such a kind of system, okay, it is termed as isolated system. Okay. Let us move to the next lecture, next question. Given the following data is for the ternary mixture A, B, C gas at a certain pressure which is 12 megapascal and temperature is 308 Kelvin. Example, there is, that means ternary mixture consisting of A, B and C, which is a temperature of 308 and pressure equal to 12 megapascal. The fraction of A, B, C in this particular mixture is 0.55, 0.2 and 0.25. In addition to fraction, the one more information is given, that is fugacity coefficient of A, fugacity coefficient of B and fugacity coefficient of C. That means the fugacity coefficient denotes non-ideality with A, B and C. The fugacity phi A cap is representing the fugacity coefficient of A in the mixture, phi B cap and C cap, that means fugacity coefficient of B in the mixture and C in the mixture respectively. The cap comes, that means when it is in the presence of others, the representation is given as phi A cap, phi B cap and phi C cap. If it is only pure A, pure B, pure C is present, this cap is removed. The fugacity coefficient of A, fugacity coefficient of B, fugacity coefficient of C. What happens? The things given the data, you have to find out what is the overall fugacity of this particular mixture. So, there is based on Gibbs energy formulation, the fugacity of this particular mixture containing A, B, C can be estimated using F is equal to P into exponent of sigma yi ln phi I cap. If you expand the sigma for the ternary component, then you get Ya phi A cap plus Yb phi B cap plus phi C cap. Using everything is provided, that means P pressure, you know, 12 megapascal, that is, I mean, you can able to find out given, and phi A cap, phi B cap, phi C cap, Ya, Yb, Yc all the given. So, you can able to find out the fugacity coefficient of mixture. So, finally, the fugacity, if you apply the data in this formula, you get 9.672 megapascal. The answer for this fugacity of gas mixture is 9.672. So, what is the, let us talk about what is the background in getting this formula, right? Let us discuss that. If you can able to see, right, this, let us take example of ideal gas mixture. Let us, because there is a container containing ideal gas, this is a container containing a non-ideal gas. What is the Ig example using, because through Gibbs energy formulation we will reach to the kind of formula. The final formula you have to reach to this formula. How we have achieved, let us discuss. The Gibbs energy of this particular entire mixture is Gig. If this mixture containing of A, B, C kind of components, the partial Gibbs energy of ith component is G bar Ig. Gig is a total, G bar Ig is the partial. Okay. This total Gibbs energy is because of the summation of this different components of I in this mixture. Okay. The Ig is representing the gas molecules are behaving ideally. In contrast to the another containing of consisting of non-ideal gas or real gas, the G is the total Gibbs energy of this particular mixture, which is formed because of different components in this mixture. So, for any ith component, G bar I is representing partial molar Gibbs energy of I in this mixture. Okay. Here you can see the difference between these two is the Ig is removed here, because it is a real gas, the Ig at the subscript superscript is removed. So, the total Gibbs energy Gig is a combination of different gas molecules in this mixture. Total pressure is P, which is because of the different partial pressures of components in the mixture. T is the temperature, P is the total pressure and Pi is the partial pressure. Because what we have dealt in this example is the non-ideal, because fugacity coefficient and everything comes from the non-ideal gas mixture. So, to evaluate non-ideal gas, you have to take the help of an ideal gas. That is why you have to compare all these two all the time. T is the temperature, P is the pressure, Pa is the partial pressure of this real gas, F is the fugacity coefficient of this particular gas. The fugacity will not be here, the fugacity will be here, and Fi cap is representing partial fugacity of every component in this real gas mixture. Phi is the total fugacity coefficient of this mixture, Phi I cap is the individual fugacity coefficients of ith components in the mixture. G, that means total Gibbs energy, G bar A and G bar B, for example A, B are present here, there will be two partial molar Gibbs energies of A and B which contributes to the total Gibbs energy. P is the partial pressure consisting of PA and PB. Fugacity coefficient Fa cap means fugacity coefficient of A in this mixture, Fb cap is the fugacity coefficient of B in this mixture. Fugacity of A and B. Phi A cap and phi B cap are the fugacity coefficient of A, B in the mixture. You can see always you have to take the help of ideal gas to evaluate the properties of the real gas. Now, difference between the total Gibbs energy of ideal gas minus total Gibbs energy of the real gas is nothing but residual Gibbs energy, always G minus Gig. Okay, you have to remove the real gas Gibbs energy with the ideal gas Gibbs energy, because I already told you that you have to take the help of the ideal gas to evaluate the properties of the real gas. So, G minus Gig is a standard formula RT ln F by P. F is a fugacity and P is the pressure. So, that is nothing but RT, here T is missing, RT ln phi cap. Okay, RT ln phi cap. Similarly, if you differentiate between partial fugacity of the real gas minus partial Gibbs energy of the real gas minus partial Gibbs energy of the ideal gas, you get RT ln Fi cap by Pa. Here it is a total pressure, here it is a partial pressure. Therefore, RT ln is equal to Fi cap by Yi into P, because partial pressure is nothing but the mole fraction into total pressure. So, difference between G bar I minus G bar I Ig is nothing but RT ln phi I cap. Phi I cap is nothing but Fi cap by Yi into P. So, therefore, fugacity of this particular mixture is F by P, and fugacity coefficient of ith component in the mixture is nothing but Fi cap by Yi into P. You have to see, if you remember the summability relationship, that means the total Gibbs energy component comes from the summation of partial Gibbs energies. So, for the ideal gas you have to multiply the Yi into G bar I Ig. For the real gas you have to G is equal to sigma Yi into G bar into I. This is for the ideal gas, this is for the real gas. If you remove 4 from 3, you get G minus Gig is nothing but sigma Yi RT ln phi I cap. Okay. Now, you take out this R, because universal gas constant and temperature are constants. So, you get out of this sigma, then G minus Gig is equal to RT into sigma Yi ln phi I cap. Therefore, you already know that what is G minus Gig? It is nothing but G minus Gig is nothing but RT ln F by P or RT ln phi. So, substitute the particular expression and equate it to this one. Then finally, you get F equal to P times exponent of sigma Yi phi I into cap. This is the formula. That means fugacity of this particular mixture is nothing but the pressure into exponent of sigma Yi ln phi I cap. We have used this particular equation to evaluate the fugacity of the mixture, right? The fugacity of this particular mixture, which is the fraction of this A, fraction of B, fraction of C, which is having the fugacity coefficient of A is 0.75, 0.8 and 0.95 for B and C. So, thank you. Let us move on to the next question. Yes, let us look into the question number 33. it is given as ideal non-reacting gases, gas A and gas B are non-reacting gases, are contained in a perfectly insulated chamber. That means it is a perfect insulation, so there is no heat transfer, right. There is a thin partition between A and B. A partition is removed and the two gases will mix and they will finally reach to the one equilibrium temperature. Okay. What is, because of this removal of the partition, the both gas going to mix. If both gas is going to mix, what is the total entropy, the change in entropy for the process? That means entropy of mixing you are supposed to evaluate. Okay. Let us find the information. That means if these are mixing, you have to find out the entropy of mixing. So, case 1 which is having example, the one side which is having A molecules, on the another side which is having the B molecules. A molecules and B molecules are at separate pressures. Okay. The volume is also different. So, in this case 2, the moment you have removed this partition, the both gases mix to each other, which comes under the case 2. You have to find out if both gases are mixing, you have to supposed to calculate the entropy of the mixing, because after mixing state, the fraction of Ya, that means fraction of A in the mixture is Ya, the fraction of B in the mixture is Yb. So, let us find out. Before the case 1, the entropy of pure A is SAIg, entropy of pure B is SBIg. So, after this both gets mixed, you have to find out the entropy of mixing. So, final entropy of the mixture is S Ya into Sa plus Yb into SBIg minus R into sigma Yi ln Yi. Okay. This is what you are supposed to find out. That means the entropy contribution in the case 2 is because of the 3 aspects. One is contribution of entropy A in this mixture, contribution of entropy B in this mixture. Third one is, once A molecules or B molecules comes together, they will try to arrange in different ways. It is not like all A molecules on one side, all B molecules on the other side, it is not possible. Okay, A and will mix with each other. Because of the mixing, even more entropy is going to get generated. You have to find out the entropy of mixing of A molecules and B molecules. Okay, entropy of mixing can be calculated using the last term, which is minus R into sigma Yi ln Yi. Entropy of mixing. So, information is given, that is, you have to find out R, which is 8.3 joule per mole Kelvin. You can take the R as 8.3 joule per mole Kelvin. You have to find out Ya ln Ya plus Yb ln Yb. So, information about the Ya is required, but here it is given Ya and Yb. Instead of directly giving Ya and Yb, they have given volume of A and volume of B. Let us find out total moles of A and total moles of B. If you know the total moles of A and B, automatically you can able to calculate the fraction of A and fraction of B in this formula. Let us find out, given the temperature, pressure and volume of the gas A is Ta, Pa, Va. So, Na, okay, moles of A in this mixture is pressure into volume of A divided by R into 2, that means in this container. If you put all the numbers which are given, you can able to find out 2.999 moles of A is present here. What is the moles of B is given with the temperature, pressure and volume informations. Then moles of B is nothing but P Vb R into T. So, Ya, that means fraction of A, once you remove, both will get mixed. In the mixed state, what is the fraction of A and what is the fraction of B? Ya is the total moles of A divided by moles of A plus moles of B. Fraction of B is equal to moles of B by moles of A plus moles of B. So, you get 0.751 Ya, 0.249 Yb. So, finally, you get entropy of the mixing is 4.666 or 4.7 joule per mole. That means you have, this is the correct answer. Then the thing is how we reach to this formula. I will explain you in a moment. Yes, and you can refer to my CET lectures in my channel where you can I have talked about this entropy. Because I have a separate channel, you can able to find out the information there. So let us depict the things. You can imagine the first container is consisting of A, second container is consisting of B. We are going to mix these two by putting some a kind of pipe in between these two. This is the same formula I am trying to explain. So before this and after mixing state is this one, bigger container, kind of molecules of A and molecules of B in this mixture. Here what you have to observe is S bar SAIG, that means pure entropy of A, SBIG is pure entropy of B. Once these both are mixed, the total entropy of mixture is SIG, which is a combination of partial entropy of A. That means once A and B are mixed, the total entropy will become a partial entropy. Fraction of A and this partial entropy of A, fraction of B and partial entropy of B. You have to use summability relationship to find out the total entropy of this mixture is a combination of sigma yi s bar I ig. Here these are both both are present, then you have to expand this sigma for A and B, ya into s bar A ig, yb into s bar B ig. So if you refer to my lectures, you are going to understand S bar A, that means partial entropy of A in this mixture is nothing but pure entropy of A minus R ln Ya. Ya means fraction of A in this mixture. Partial entropy of B in this mixture is a pure entropy of B minus R ln Ya. So if you substitute this in the summability relationship, you will going to find out total entropy is Ya into SAIG plus Yb into SBIG minus R Ya ln Ya minus R ln Yb. So if you combine these two terms, you get R into sigma Yi ln Ya. So the contribution of pure A is Ya into Sa in this mixture. The contribution of B is Yb into SBIG. Once A and B molecules comes in the container, they both mix with each other, which generates additional entropy, which is called the entropy of mixing. That particular entropy of mixing is the third term. So we have used this particular term to evaluate entropy, which is comes to be around 4.7 joule per mole. Thank you. Let us move to the next question. Yeah, it's a question number 48. Right, an ideal monoatomic gas is contained, that is in the cylinder piston assembly, connected to a Hookean spring. You can see this is connected to a spring, and this is the system containing of monoatomic gas, which is having some piston. The piston is frictionless and massless. That means he is talking about the ideal process. The spring constant is 10 kilonewton per meter. At equilibrium at initial equilibrium state, that means before expansion of the cylinder, the spring is unstretched, that means the spring is in this particular position, right? And if what happens, you supplied heat through this filament, okay, that means total amount of heat that is supplied to this particular system is 362.5 joules of heat. If you supply the heat to the system, this particular cylinder or this stopper will expand and will touch these two stoppers. The piston passes through a certain distance and it will stop at this particular point. If that is the case, you have to find out after stretching what will be the final temperature of this particular gas. Okay, then the distance it is moved is 5 centimeters. Okay, the outside this piston, it is at an ambient pressure 1 bar. So let us find out the initial temperature, initial volume is 2 liter and 300 Kelvin. After expansion, you have to find out what is the temperature change of this particular 300. From 300, let us find out how much at the final point the temperature of this particular system will be. So, in this kind of examples you have to go for the first law thermodynamics, right. Through that information you can able to find it. The first law, that means before expansion, after expansion, that is the state 1 is the before expansion, state 2 is the after expansion process. Before and after, let us apply the first law. The first law, because it is a closed system, because it is a fixed gas containing in this particular cylinder which got expanded. So, let us apply the first law for a closed system. The change in internal energy because of the change in state 1 to state 2 is nothing but how heat that is supplied to the system or work that is supplied to the system, okay, plus or minus Q and plus or minus W. When to use plus, when to use minus. If you supply anything to the system, it is taken as positive. If you remove anything from the system or system does something to the surrounding, you have to take it as a negative. Anything towards the system is positive, anything from the system is negative, whether it is a heat or work, anything, any energy. So, heat is supplied to the system. So, whatever the value of heat, which is 362.5 kilojoule, is a positive, you have to take it as a positive number. System got expanded. Because of this expansion process, it does two things. One is it is pushing the spring to the right side. That means system is doing some work on the spring. The second work is, see, outside the system it is at an ambient pressure 1 bar. If the system got expanded, that means it has done some work against the surroundings. That means there are two works done by the system. One is against the spring, second is against the atmosphere. That means the work come from the total work come from the two different works, which has to be taken as a negative because the system does work to the surroundings. So, you have to apply. So, change in internal energy, that means before and after, it is nothing but delta U. The change in internal energy is plus Q and minus 2 works here. Okay. What is change in internal energy? For an ideal gas, the change in internal energy for a closed system is taken as NCV dt, okay, because for ideal gas Cv is constant, it is not changing with respect to temperature, it comes out of the integration. If it comes out of the integration, delta U is nothing but NCV integral T1 to T2 dt. T1 is the initial temperature, T2 is the final temperature. So, delta U is equal to NCV T2 minus T1. So, you got one side of the expression. Let us find it another side of the expression. Q is nothing but taken as a positive, which is 362.5 joules, and work, two works, which both works are, you have to take it as a negative. So, the first work, that is against the surroundings, that means P, it has done displacement work against the surroundings, it is pushed the surroundings to against this particular pressure. So, the work done on the surrounding is, the surroundings is at 1 bar pressure, the change in volume is delta V. So, P into delta V is the work done by the system on this particular surrounding, and delta V is nothing but area of the cylinder and the distance moved, okay, that is A into delta L. The second work is done on the spring. So, second work is half into K into delta L square. This is the work done on the spring. K is the spring constant, which is given as 10 kilonewton per meter, and delta is the distance moved, that is 5 centimeters. That means you got all the information, simply you calculate the work 1. Make sure you have used SI unit, convert the things into the SI units. The first work is half into 10 into 5 into 10 power minus 2 whole square, and the second work, okay, say first work is 50 joules, second work is 12.5 joules, both are, you have to take it as a negative, okay. So, let us apply everything in this formula. You substitute in place of delta U this particular equation, in place of Q this particular number, in place of W these two particular numbers. What is the information which is not given is the value of Cv, okay. For an ideal gas, monatomic gas, the Cv is nothing but 3 by 2 times R. R is the universal gas constant, which is 8.314 joule per mole Kelvin. Substitute in place of Cv 3 by 2 R. N is the number of moles of gas. So finally, if you substitute everything in this formula, N into 3 by 2 R, T2 minus T1 is nothing but 362.5 minus 50 minus 12.5. From this you get N into 12.471 into T2 minus T1 is equal to 300. Then you don't know N here. You know T1. T1 initial temperature, it is given 300 Kelvin. That means in the moles, you don't have any information about the moles. Simply use the information that during the state the moles or gas is not changing, only it got expanded. So let us find the moles of the gas. PV equal to nRT, N equal to PV by RT. In the state 1, before expansion, I know the pressure, I know the volume, I know the temperature, all the information provided, and therefore the P is nothing but, N is nothing but PV by RT, that is 0.0801 mole. Okay. Initially it will be 1 bar pressure, so that is why you have taken P equal to 100 into 10 cube Pascal. So finally you got N. So using this formula, find out the value of temperature T2 after the expansion is 600 Kelvin. Okay, this is how you can able to find out, because this particular example frequently given in the gates, that Hookean springs, the Hookean springs, work from the Hookean springs can be calculated using half into K into x square. X is the distance between the before expansion and after expansion. So I hope how to apply the first law for a closed system for this kind of situation. Let us move to the next question. This is question number 61. The question is given as methanol is produced by the reversible gas phase hydrogenation of carbon monoxide. CO and H2 are charged to the reactor and the reaction proceeds to the equilibrium at 453 Kelvin. That means after the reaction, the final temperature is reached to the 453 Kelvin and 2 atmospheric pressure. That means inside the reactor you have the temperatures of temperature 453 Kelvin and pressure is 2 atmosphere. And the reaction equilibrium constant, which depends only on temperature, that means for every reaction there is an equilibrium reaction constant for reversible reactions. It is given as 1.68 at the reaction conditions. That means at temperature reaction conditions, that 453 Kelvin, the equilibrium constant value is 1.68. The mole fraction of hydrogen in the product is 0.4. That means at the end 3 things will come out: unreacted carbon monoxide and unreacted hydrogen, okay, and methanol. Okay, these things will comes out. Among these products, the hydrogen in this at the exit is around 0.4. Assuming ideal gas behavior, the mole fraction of methanol in the product, okay, you have to find out if 3 things are coming out. Among the 3, hydrogen fraction is 0.4. You have to find out what is the methanol fraction. This is how we can able to simplify. Given the main equation to find out the relationship between the mole fractions and equilibrium constant is pi I yi power Vi is equal to p power minus V into K. K is equilibrium constant, V mu I, that is this kind of Vi is the stoichiometric coefficient of this any particular component, and what is V? It is a total stoichiometry of the reaction. So let us see one by one term in this particular equation. Let us take the reaction. The reaction given as 1 mole of CO plus 2 moles of hydrogen gives rise to 1 mole of methanol. So the stoichiometric coefficient of carbon monoxide is -1, the stoichiometric coefficient of hydrogen is -2, the stoichiometric coefficient of the product methanol is 1. The stoichiometry of the reaction means addition of all the stoichiometry of the components. That means stoichiometry of monoxide plus stoichiometry of coefficient of hydrogen plus stoichiometry coefficient of methanol. So -2 -1 plus 1 gives rise to -2. That means the total stoichiometry of the reaction is -2. So let us expand this particular equation. The product of yi power Vi. How many components are there in this participating in this? One is CO and H2 and methanol. So, you have, if you expand this particular term, you have to product of 3 particular terms. One is y of fraction of carbon monoxide power stoichiometry of carbon monoxide, and fraction of hydrogen power stoichiometry coefficient of hydrogen, and fraction of methanol power stoichiometry coefficient of methanol, which is equal to p power minus v, that is minus of this minus 2 into k. K is the equilibrium constant. So, altogether you get the information, the fraction of CO power minus 1, fraction of hydrogen power minus 2, and fraction of methanol power 1 is equal to p square into k. From this expression you get fraction of methanol by fraction of carbon monoxide is equal to p square, that is a pressure square, into the k, which is called equilibrium constant, into fraction of hydrogen square. That means, if you can able to get the fraction of methanol which is required for this question from this particular equation. And you know all the right hand side terms, which is pressure which is given, and equilibrium constant value is given, fraction of hydrogen is given. If you put everything here, you get 1.075. Okay. Then sigma, you already know that fraction of all the components will be equal to 1, sigma yi equal to 1, that is fraction of CO plus fraction of hydrogen plus fraction of methanol equal to 1, because only 3 components are present at the end. So, among that, fraction of methanol is 1 minus fraction of hydrogen minus fraction of carbon monoxide, that is 1 minus 0.4, which is minus this one. So, fraction of methanol is nothing but 0.6 minus fraction of carbon monoxide. Now, you substitute the fraction of methanol in this particular equation, you can able to find out fraction of carbon monoxide is nothing but 0.2891. So, you know the fraction of carbon monoxide, you know the fraction of hydrogen, which is 0.4. From this information you can able to find out the fraction of methanol. The fraction of methanol is 1 minus fraction of carbon dioxide minus fraction of hydrogen. So, that is in total 1 minus this 2 terms, you get the fraction of methanol in this mixture at the end of the reaction is 0.31, which is 31%. I mean there is a specific procedure to get this equation, but it is a standard equation. If this is a non-ideal gas, this fugacity coefficient will be included here. I will explain you how, I mean if the fugacity, how, because this equation is valid for the gases. If the similar kind of equation, it can be valid for the liquids. The background to get this expression, I can explain you using this. The concept originates from chemical reaction equilibrium. This is the base equation from where you can able to get that particular equation, which is used in the solving the problem. Fi cap by Fi0 power Vi equal to k. K is nothing but which is the exponent of minus del G by RT, which is equal to exponent of minus Vi Gi by RT. This is the standard expressions people use while dealing with chemical reaction equilibrium problems. So, this particular expression can be applied to the gaseous phase, or this particular equation can be applied to the liquid phase. Okay. That means only thing, the difference is how we can able to get the equations for fugacity for the gas phases and fugacity for the liquid phases. Once you substitute in this particular expression, the different equations will emerge. You have used this particular equation because we have dealing with the gas phase. If this is the equation you are supposed to use if you are dealing for the liquid phase, that means both are equations used for the ideal gases and ideal liquid. For non-ideal gases, there is another expression you can use for the non-ideal gases and liquids. For example, if you take this particular expression, you wanted to use it to apply for the gas phases. So, let us evaluate one term by one term. What is the fugacity coefficient of I? That means ith component fugacity in the gas phase is nothing but phi I cap Yi into P. Phi I cap is nothing but fugacity coefficient of I in the gas mixture. Yi is the fraction of component Y in the mixture, P is the total pressure. When you come to the gases, Fi0 means pure gas fugacity of I. That means always you have to get this particular term. For gas phases, it is assumed, it is standard state is Fi0, which is nothing but fugacity of coefficient of pure I at the same temperature of the mixture is nothing but 1 bar. For ideal, so this particular equation you are supposed to use for the non-ideal gas mixtures. But for ideal gas mixtures, the fugacity coefficient value will be equal to 1. So, this is the equation pi I yi into p power vi equal to k. What is vi? If you expand this particular term, so pi I yi power vi into, you can take p out of this term, you get pi I into pi power vi. Pi power vi means product of, if it is a 4 molecules present in the reaction, you have to take the product of these 4 terms, p power va, p power vb, p power vc, p power vc. va, vb, vb, vc are the stoichiometric coefficient of a, b, c, d respectively. So, once you get this p, you bring it to the right hand side. va plus vb plus vc plus vd is called stoichiometry of the reaction, which is v. That is nothing but, if you take this pressure term to the right hand side, you get pi I into yi power v is nothing but p power minus v into k. This is the equation which is used for assuming the ideal gas. If it is a non-ideal gas, you have to use this particular equation. If they have given the fugacity coefficient informations, you can able to deal with it. And this is for the liquid phase mixtures. And for the liquid phase mixtures, it is the standard state fugacity is not 1 bar, you have to separately calculate. Okay, standard state fugacity of I, that means you have to use this equation for the liquid phases. So, fugacity IAG represents the fugacity of the pure liquid at temperature and pressure 1 bar. This is the standard state that is assumed for the liquid phases. Now, Fi cap is equal to, here it is phi I cap yi into p, here Fi cap is nothing but gamma I xi into Fi. Gamma I is the activity coefficient, that means fugacity coefficient, that means non-ideality in the gas phase is represented by fugacity coefficient, and non-ideality in the liquid phase is represented by the activity coefficient. Here it is yi, here it is xi, is the mole fraction that is representing in the liquid phases. And substitute this particular term in this equation, you get pi I into gamma I xi Fi by Fi0 power vi equal to k. So, what is Fi by Fi0? Fi by Fi0 is very standard, fugacity of I divided by fugacity of its standard state. Okay, is nothing but exponent of 1 by RT into P0 to P Vi into dP. This particular V is the volume of the, molar volume of the component I. Okay. You substitute this expression, because very standard expressions given in the textbooks, you can refer to the Smith and Varnes, and you can able to find this particular expression. Once you got this expression, you substitute in this above equation, you are going to find out that pi I gamma xi exponent of volume minus p0 by RT power Vi, okay, is equal to k. In general, when you apply this particular expression for the at very low pressures, this expressions, okay, will be exponent of volume times p minus p0 by RT is equal to 1. In majority of the cases, this particular value of this particular term equal to 1. So, we are neglecting. So, final equation is pi I gamma I xi power Vi equal to k. That means you have to use this particular expression for the non-ideal liquids. If it is liquid is behaving ideally, the activity coefficient value equal to 1, then final expression is pi I xi power Vi equal to k. This is the equation you are supposed to use for the ideal liquids. This is the equation used for the non-ideal liquid, ideal gases. This is the equation used for the non-ideal liquids. This is the expression used for the non-ideal gases. So, in majority of the gases, people will refer to the ideal gas in the problem. So, you can remember this, this, this and this. If you can able to remember these 4 expressions, you can attempt many of the problems in the GATE. Thank you. That is the end. Thank you.